Wow, what a great crowd. Thanks for coming today. Thanks Usama and Rajesh for inviting me. So as Usama said, I want to talk about social science today, which may not seem very applied, but I hope that in the course of the next sort of generation, the kind of work that I'm going to talk about today will become more applied and more industry relevant. So I'll start by, most of you are not sociologists, so you might be curious like what social science is really about or what sociology is about. And for me, what I've always found fascinating about sociology is that it is fundamentally a study of emergent phenomenon, that you bring people together and they interact with each other in complicated ways and they influence each other and they pass information to each other, and then something happens that's almost magical, where they become a family or a firm or a political party or a market or an entire culture, and they have these properties that we sort of talk about as if they belong to individual actors. But of course, these properties are really emergent properties that come through these complex networked interactions. And so this is a phenomenon which sociologists call the micro-macro problem. It's really been around for as long as sociology has been around, but there's always been a problem in trying to understand it, which is that empirically it's very difficult to get a grip on. And that's very easy to see in a data science crowd. I think you can be sympathetic to this, that even just to observe thousands or millions of people interacting with each other over time, that's already a tremendous amount of data to be able to collect, and historically it's not something that social scientists have been able to collect. And then if you want to do more than just look at correlations, if you want to understand what is causing things, you have to do experiments, and that's even more difficult to do, especially when the experiments involve people. And so if you take away the ability to measure things and to do experiments, that really is sort of 2/3 of the scientific method. And so I think that probably explains why in social science we have lots of theories and we have very little ability to decide which of those theories is correct. And so what is so exciting to me about this particular era of social science is that we're just starting to see these historical barriers that have been around for about 100 years now lifting. And really it's been the technological revolution of the internet and digital communication that has been driving this. And the trend, I want to talk about a couple of trends today. The one that gets most of the attention is the big data trend, where in the course of everyday activities, people are sending emails, participating on social media or networking sites, generating an enormous amount of data that is essentially social data and that is helpful to us in understanding what people are doing and possibly even why they're doing it. But also, and this has received somewhat less attention, at least in the media, is the idea that you can do experiments, not just A/B tests, but traditional lab-style experiments of the sort that have been going on for generations in psychology labs, but on a much larger scale and with much more representative people. And so if you put all this together, what we've been seeing for the last decade is the emergence of what is now being called computational social science, this sort of intersection between the social sciences where the questions are coming from and the applications are coming from, but involving a lot of thinking and methodology from the computational sciences. So I just want to illustrate this idea of computational social science with a couple of examples, and I'll try to get through two of them. One of them is something that will be familiar to many of you, looking at social contagion using digital data, and the other looking at how people solve problems in teams using a virtual lab experiment. And so these are, I just emphasize, these are both very old questions, and pretty much all of the research that I do, at least, is related to questions that are old questions in social science, things that have been around for how do things spread, why do people cooperate, how do people collaborate together, how do organizations work. These are questions that have been around for decades, if not centuries. And what is different is that we have new classes of data to bring to bear on these questions. And I probably won't have time to talk about the challenges, but there's certainly something that I think this research illustrates, and maybe we can talk about that afterwards. Okay, so social contagion is a popular topic at KDD. I won't sort of belabor the point, but I think when people who work on this from the modeling side think about social contagion or really any kind of contagion, this is the mental model that we have in our minds. And this mental model comes from biological models of disease spreading, where an individual, a single person, like the red dot in the middle here, gets Ebola in West Africa and passes that disease to a small number of his family members or close neighbors, and each of them passes it to a small number of their close neighbors, and so on. And you get this spreading process that grows exponentially through a many generations of a branching process, where at each branch there's only a small number of new people getting infected, right? And so this is a very common assumption in it's pretty much all of the mathematical models that we use to study biological disease. And at some point in the 1960s, those models really just got carted over to the social sciences and repurposed to describe product adoption and increasingly other types of social contagion. So I think it's fair to say that when we talk about social epidemics or things going viral or things diffusing online, this is what we think is happening. The problem is that what we see is this kind of data, where you see aggregate counts of things over time. So these are sort of famous papers from the 1950s and 60s, Coleman, Katz, and Menzel studying the spread of tetracycline among doctors in the Midwest, and Everett Rogers' famous book, Diffusion of Innovations, which is maybe the most cited book in all of social science. And they both have this characteristic where if you look at things over time, you look at aggregate counts over time, you see these characteristics S-shaped curves. And Rogers claimed quite explicitly that it's the shape of this curve that implies diffusion, that you see this sort of slow takeoff, and then you see exponential growth, and then you see saturation, and that's how you know that you're looking at diffusion. And this is old data, but I think if you looked at things like YouTube counts over time, you would get similar types of data. Now, there's a big problem, or rather two problems, with using S-shaped curves to infer diffusion. And one is that there's lots of ways to get S-shaped curves. So there's not only lots of diffusion models, but there's lots of models that involve no diffusion whatsoever. They can also generate S-shaped curves. You can just assume that there's some sort of distribution of propensity across the population, or you can throw in things like mass media and marketing efforts, and you can get any shape curve that you want, including S-shaped curves. And the other problem with S-shaped curves, and this is sort of one of those sort of subtle and obvious points that is both subtle and obvious at the same time, is that when people, researchers look around the world to find things to study, they typically focus on interesting things, right? So why would you study uninteresting things? Of course you only want to study interesting things. So when it comes to diffusion researchers look at things that diffuse. They look at practices that are successful. They look at books that are successful. They look at memes that are successful. And they never look at the things that nobody ever did or talked about, and the things that never spread. But of course, that's sort of a classic error of selecting on the dependent variable. If you want to understand why people are successful, you can't just go and talk to successful people, because of course, there are lots of things that successful people do, like getting up and having breakfast in the morning, but that is not necessarily predictive of being successful, because unsuccessful people do that as well. And the same thing happens for diffusion events. So if we want to understand what's going on with social contagion, we really need two properties of our data. One is that we want to see things spreading at an individual level, like that picture that I showed you. And the other is that we want a total sample of the population. We want to see everything that could potentially diffuse, as well as the things that actually succeed. And that turns out to be the vast majority of everything. Okay, so of course, the web helps us with this. It's not perfect, but we have about 10 years now of interesting papers that use digital online data to study diffusion. And so now that we have this kind of data, we can ask new questions like, how much of diffusion is viral anyway? And when we see something spread in a way that we think is viral, what does it look like? So I'm going to talk about a couple of projects. This is work done back at Yahoo Research with Sharad Goyal, who's now at Stanford, and Dan Goldstein, who works with me at Microsoft Research. And we took a bunch of projects that either we had worked on or that other people, our colleagues at Yahoo, had worked on that were in many ways unrelated. They were about different types of online platforms, one on Facebook, one looking at a synchronous video viewing app that one of our colleagues had built, one looking at Twitter data, one working with the Yahoo philanthropic team to build a kind of pay-it-forward fundraising campaign for the holiday season. The only thing that they had in common was that they all had a kind of social referral mechanism built into them. That in every case, people were trying to get these things to spread virally through some kind of network. But the networks were different, the adoption process was different, the platform itself was different. And these differences are actually just as important as the similarity because every single one of them has various kinds of biases built into them. So whatever you find by looking at one particular example could just be an artifact of the peculiarities of that particular data generating mechanism. And so if you pick a bunch of different data generating mechanisms and you find the same empirical regularities, then it's possible that those regularities are robust. And so that was the hope that we went in with. And in fact, there's a tremendous amount of similarity across these different applications, these different domains. So we have 6 different domains here. And what this picture is showing is the 5 most frequent patterns that we see. So a dot means that somebody introduces a new thing and it doesn't go anywhere, right? And a dot, a little dyad, a little barbell symbol here means that one of your friends adopted the thing. And if you have 2 children in these little trees, that means there's 2 adoptions. And then if you look at this, if you take the Twitter example over here, so this means this one on the right-hand side here means that you tweeted out something, one of your followers retweeted it, and one of their followers, who's not one of your followers, retweeted it. So that's starting to look a little bit like what we might think of as viral diffusion. But notice that in Twitter here, 93% of things that are tweeted out never get retweeted. And so if that's your experience of using Twitter, that you tweet something and it just sort of falls into the abyss, you're in good company. It's true for almost everybody, just like most of the papers that we write. So you can actually summarize this figure even further and say, if we look at everything, we lump all of the data together, it turns out that about 90% of all events consist of people introducing something and nobody paying attention. About 8% get 1 additional adoption. About 1% get 2 additional adoptions. And everything else, everything you've ever heard of, every viral cat video of cute babies, every best-selling book and blockbuster movie, everything is in that little blue bar on the right-hand side. So 99% of events are in look like one of these 3 motifs here. So if you had a very stupid model of diffusion that said, 90% of the time this happens, 8% of the time this happens, 1% of the time this happens, you would correctly classify 99% of everything that's happening. And you might say, well, okay, but I don't care because I know that in this little blue bar here are really, really big things. So, like the Spanish flu in 1918 infected 1 billion people. So if you look at all the cases of influenza ever, a large fraction of them were in this single event. So it's a really rare event, but it's so big that it still matters. And so we can make a stronger statement and say, well, there's nothing like the Spanish flu in this data. That in fact, 99% of all adoptions, if we count all the adoptions over everything in every tree, 99% of them are within 1 hop of the seed. So most...
You point with the mouse because the other screen...
Oh, right. Most viral is not... the mouse. Oh, I see. Yeah, okay, great. So, yeah, so most of what we think of as viral spreading is not really viral at all. So if you're like other people who we told this result to, they say, well, we're still not convinced because our gut tells us that guts are getting a bad rap today, that there are these big things out there, right? Does anybody not know what this is? I gave a talk at Cornell, which is up in Ithaca, New York, and one guy there, Paul Ginsberg, who started the archive, he did not know what Gangnam Style was, so that says something about Ithaca, or maybe Paul Ginsberg. Okay, So this thing now has 2.6 billion views on YouTube. And so surely this is viral, right? We know these things are out there because they're so big and they're so impactful. But is it viral or is it just popular, right? You know, the Super Bowl gets about 100 million views, and nobody would call the Super Bowl a viral event. It's a broadcast media event. It looks like one of these hub and spoke things here, where you've got a single node in the middle and a large number of nodes, children nodes, are attached to it, but nothing else is happening. And so really all we know about Gangnam Style is that a lot of people saw it in a short period of time, but you know, maybe they all came through yahoo.com or some other mass media site. So to test for this, we took an even larger sample of data. All of this is from Twitter now, over a 12-month period, sort of roughly speaking, every video, news story, image, or petition posted to Twitter over the period of years. So if there's anything viral going on, we're going to see it. And so then, to address another criticism of our first paper, that we just simply hadn't looked at interesting stuff. So of course you didn't see anything going viral. We threw out everything that was arguably not interesting, right? So we restricted to only events that got at least 100 retweets. So 100 retweets is already way more than anything I showed you on the previous slide. So this is sort of 1 in 3,000 events gets 100 retweets. So these are already super rare things. But because we have over 1 billion things to start with, we have about 350,000 of these rare events. And so now for each of them, we can quantify what we call its structural virality. So this is a little different from the normal notion of virality. Imagine that you have a thing spreading, and it looks like this. So you have a single node, broadcast something out, a bunch of people retweet it, and nothing else happens. We just treat that object as a graph, and we compute its average pairwise shortest path length, and that is roughly 2. Okay, so the lower limit of structural virality is close to 2, or asymptotically 2, and that is what you get for a broadcast. At the other extreme, if you have a very viral-looking thing, which is this sort of classic multi-generational branching process, then the depth of the tree is going to be log n, and so the shortest path length is also going to be proportional to log n. So you get some number for each one of these events that's somewhere between 2 and log n, and now you can ask for different, if we take a large sample of them, how much diversity do we see with respect to structure? If we look at large popular things, what do they look like? Are they mostly broadcasty, or are they mostly viral? Or are they somewhere in between? Is there some kind of optimal combination of broadcast and viral that somehow makes things spread? And so I'll ask you to sort of privately guess which one you think is correct. And then finally we can ask, well, how does this relationship change as things get bigger? So the answer to the first question is whatever you guessed is correct. We see everything. We see everything from super broadcasty things. So this is this black triangle is a CNN story where CNN tweets it out, and a lot of people, this black triangle is just a lot of lines, about 100 people retweeting it. And then as you go across from the top left to the bottom right, you see things becoming increasingly viral. And what's interesting about these figures is that they all have about the same number of nodes in them. So they're roughly the same popularity, but they vary dramatically in terms of their structure. The other interesting thing is that if you look at the insert here, this is sort of the old school data that you would have gotten back before you could see structure, where you're just counting number of retweets over time, and you see these things, with the exception of this weird one in the middle here, all look very similar. So there's no way you could discriminate between these different structures just by looking at the aggregate data. And then the second question, how does this structural virality change with size? And the answer is it doesn't really change very much at all. So we've now broken things down according to the 4 domains that we looked at. And for 3 out of the 4 domains, there's essentially 0 correlation between size and structural virality. And what's going on here is that, and also particularly for pictures and videos, the median structural virality is way down near the theoretical minimum, near 2. So basically what's happening here is that everything is being driven by the size of the biggest broadcast. And this is particularly true for pictures and videos, because if you look at Twitter, the most followed people on Twitter are all celebrities, and celebrities don't really tweet about the news or much of anything other than themselves. And so it's a lot of pictures and videos. And so when Justin Bieber tweets out something, 70 million people see it, and that can provide a huge boost. So what do we learn from looking at this data? Well, so an interesting kind of meta-theoretical point here is that if you look at this long literature of modeling social contagion, it really focuses on this notion of the epidemic threshold, that there's a critical value of the infectiousness above which a disease spreads exponentially and below which it dies out. And if you're an epidemiologist, you want to keep things below the epidemic threshold. And if you're a marketer, you want to get it above the epidemic threshold. But everybody is interested in how do you, what are the factors that contribute to this threshold. And we find that that's sort of largely irrelevant, that everything that we are seeing is below this threshold. And everything is dying out all the time. And even the big things are dying out all the time. And the only thing that's sustaining them is these occasional, the occasional boost that they get from these very, very large nodes, which don't really have an analog in biological epidemics. So this sort of, I think, should give us some, not so much cause to throw out the models that we have, but maybe to look at at a different range of parameters for the models that we have, and to give new kinds of empirical tests to see which models are useful and which models are not. And even in sort of a more applied realm of marketing, I think it should give us a new way of thinking about how things are spreading and the value of what we talk about when we talk about viral marketing. And finally, I'll just say, there's been a lot of, in my world where you sort of have computer scientists and social scientists mixing, some people are very enthusiastic about big data, and then everybody sort of piles on and says, no, big data is not as useful as you think. This is an example where it actually is useful. If you're looking at rare events, you really need to have a large number of events in your initial population to begin with. Okay, so I want to move along to the second question, which is completely different, about how do groups of people solve problems together, and in particular, how does their ability to solve problems depend on the size of the team, the number of people involved? And Jonathan made a great point earlier this morning about how, depending on sort of which version of your intuition you use, you can convince yourself of any outcome that you want. And this is true of essentially every problem in social science. So if you read certain books like Adam Smith, you can convince yourself that the more people there are, the better off you'll be, because you get division of labor and returns to specialization, and that's why we have firms. If you read the more recent literature on social networks, you can also convince yourself that having other people around is good, because then you can learn from them and you don't have to reinvent the wheel every time yourself. But if you read a different literature in social science, you can convince yourself that exactly the opposite should be true, and that the more people you have, the less everyone's going to work, the more free riding there'll be, and also the more kind of groupthink and herding you will find. And so this is very hard to resolve with observational data, and we know this if only because the Google Analytics people have been trying very hard using observational data to figure out what predicts team performance, and it's extremely difficult to do because there's always all these confounders in the real world, so you'd really like to be able to do experiments. Of course, experiments are also hard, but one thing that's changed in recent years is that, as I mentioned earlier, we can sort of migrate this old model of the psychology lab online using crowdsourcing sites like Amazon's Mechanical Turk. And so the problem that we looked at is a relatively recent problem. It's called crisis mapping, and it began back in 2010 during the Haiti earthquake, when a bunch of online volunteers decided to monitor all of the social media posts, particularly Twitter posts, that were coming up off of the ground in Port-au-Prince, Haiti, and filter them and collate them and put them on a map, geolocate them, put them on a map, and then gave this map to the UN, in particular to the UN OCHA, the Office for Coordination of Humanitarian Affairs. And UN OCHA found this extremely useful because this is very hard for them to know in real time where everything is happening. And so crisis mapping was born as a sort of industry. And we got some of the data from a couple of different crisis mapping deployments, not the Haiti deployment, but a later deployment of a hurricane or a typhoon, Pablo, that hit the Philippines in December 2012. And this is work with Andrew Mao, who's a postdoc at Microsoft Research, Winter Mason, who's at Facebook, and Sid Suri, who works with me at Microsoft. And so what you're looking at is a group of 28 Turkers who came together on a particular day in August 2014, and they were shown about 1,500 tweets that were real tweets that were produced by people in the Philippines during this typhoon. And most of them are rubbish. They're just, people talking about, the typhoon and isn't this bad, or mentioning news stories. Nothing very directly relevant, but a small minority of them are referring to actual incidents of damage on the ground, washed out bridges and roads, flooded crops, displaced people, damaged buildings, information that's interesting and useful to the UN. And so their job was to go in there and do exactly what the crisis mappers had done, which is find this small number of informative tweets and classify them and annotate them and geolocate them and create this map that you're looking at that's emerging slowly here on the right-hand side. And they did all of this over the course of 1 hour. And you can see that in this chat room here, they're busily chatting to each other, trying to figure out, like, what are they supposed to be doing? So if you look, how did they do? Well, they did pretty well. So on the left-hand side is the actual standby task force deployment, where they spent 12 hours in December 2012. And on the right-hand side, you see what 16 Turkers did in a single hour a couple of years later. And these things are broadly similar. The difference is that we have a very highly instrumented environment, a very controlled environment, so we can record every single mouse click, every single action taken by any worker, and we can compute all sorts of interesting things about, what they were, which type of task each worker was mostly doing, and who they were connected to in terms of their communication and collaboration. And in fact, we didn't have one group of workers. We had 47 different groups of workers, and we brought them onto this platform that Andrew Mao built called CrowdMapper. And we randomly assigned them to groups of different sizes, from 1 up to 32. And then we compensated them based on some combination of their individual and group effort. So we want to understand, we're experimentally manipulating the size of the team. You want to see how does it affect performance. And the way we did that was we put together all of the maps that came out of this exercise, and we created a gold standard map. And then we measured each individual team's map against that gold standard map in terms of using precision and recall. And then because both false positives and false negatives matter, we really just focus on this F1 score, but I'll show all three. So here's the sort of first high-level result, which is bigger teams tend to do better. But there's very strong diminishing returns to scale here. So it's sort of unclear whether you actually want to have a big team doing it or whether you want to have a lot of small teams working, or even individuals working. Interestingly, this red line here is the performance of the actual standby task force. So you can see that we're getting up to comparable performance for the large teams. So you might wonder, well, why are we seeing these diminishing returns? Why is it that on a sort of per capita basis, individuals are so much more productive than people in teams? And so this result here sort of verifies what you might suspect, which is there's a lot of free riding going on, that people, or apparently free riding going on, that people in teams put in less effort in terms of the number of actions that they're taking per minute than people who work alone. But another interesting thing is that they allocate their effort differently. So if you split this effort among different types of work, the individuals are spending a lot more time classifying events, whereas the people in teams are spending a lot more time just filtering out tweets. And it's easy to see why, if you try to do this exercise, it's like that filtering is just cognitively easier to do. So sort of an interesting kind of free riding where you're not necessarily not working, but you're kind of doing the easy thing. And it turns out that the hard thing is the thing that needs to be done. So you might say, well, that's easy. We should just use small groups of people because people get lazy in teams. But that's also oversimplifying things because people in teams collaborate more as well. They spend more time working on each other's tasks. And of course, that's impossible if you're the only one doing it, but this trend increases even as group sizes increase. So what we want to be able to do is compare groups of different sizes in an apples-to-apples way, because there could be something important happening in this collaboration effort. Mostly that there's if a lot of people working independently are producing redundant effort and making errors, somebody else then has to do the work of weeding out those errors. And so that's a lot of what they're doing in these teams. So to show that, we compared the actual teams with synthetic teams, where we put together the maps of independent workers and treated them as if they were a group. And so now you see an interesting result here, that the blue line here is the synthetic teams. And you can see that they're getting better up to about n equals 8. But then they start getting worse. And the reason they get worse is that their precision gets hit, because there's too many sort of multiple copies of the same thing floating around. And if you look at what the conversations between peoples in the teams, they're actually focusing on this, where they're recognizing, oh, these two events are really the same event. We should merge them and have an argument about which one is right. The thing is, that takes a lot of time. So they take a hit in terms of their superficial productivity, but the end result is actually a more useful map. So what do we learn here? Well, individuals work harder by themselves than they do in groups, just as psychologists have been saying for decades. But they still do better in groups. So there's an interesting kind of conflict between different theories of group performance, and you have to look at a complex task like this to be able to see how they wash out. This sort of the observation that our largest groups were pretty much as good as the real thing, I think, is a striking demonstration of external validity, which has been a huge problem for lab experiments, where you can sort of test interesting science theories in labs, but when you try to generalize them to the real world, you have absolutely no idea how to do so, because everything is different in the real world. So we're really trying here to bridge the gap between lab-like control and naturalism, so that we can have results that actually generalize in practice. Okay, so just quickly summing up, I mean, there's lots of things we don't know, almost everything, in fact. So there's a whole kind of pipeline of work to be done here. If you're interested in doing some of it, I'd love to talk to you. At some point, we'd like to be able to even deploy this platform in the field. I'll just conclude by saying something a little bit sort of critical, which is that there's been a huge amount of interest and effort at places like KDD and other computer science conferences, and increasingly interdisciplinary conferences, where we're publishing lots of fascinating research. I don't really see much impact on policy, and this I think is maybe even more jaundiced view than Jonathan had this morning, that the kinds of problems that we all sort of got into doing this for, we have not made much impact on. And so I think that there's a lot of work to be done in computational social science in sort of rethinking what are the questions that we're asking, what are the kinds of collaborations that we have to put together in order to answer those questions between social scientists and computer scientists. What is the kind of data that we need to collect? What instrumentation do we need to build to collect it? So with that, I'll say thanks very much. Yeah, so the question is, we have lots of papers written about Twitter data, but at the end of the day, we don't really care about Twitter. How do we sort of, find, data for more real-world things? And I think that is, that's a difficult. I mean, that's the right question to be asking. And I think, that a lot of it is that we may have to. Well, so some of it's happening naturally, right? So you have these fitness bands that are generating digital data, which is arguably more real about how much people run and exercise and so on. So you can sort of port some of the same methodologies over to other applications as we get new sources of digital data. But I think ultimately we have to build our own instruments. We can't rely on just successful social media companies to generate data for social science, we may have to actually actively think about going out and collecting the data that we care about, and that's actually a huge challenge for social science because we just haven't really been. That's not institutionally how we've been set up for many years.
Other questions? Reminder everyone, the session is still going, so please be quiet. Other questions? Yeah, at the mic.
Hi.
Yes,
Hello
hi.
from Skype. So big team helps, but have you looked at the diversity in skills, like how they are different in the skill set?
In the problem solving task.
Yeah,
So how diverse are the people, or how diverse are
the skill set, right? In this, I know means big teams help, but if there is diversity in skill set, are they as collaborative, or if that increases?
So one answer to your question could be, what is the if we just observationally look at the data that we're getting, how does diversity of effort correlate with performance, right? And we don't actually see a very strong signal there, which is sort of interesting because we thought that, there would be, teams where kind of everybody did the same thing would do worse than teams where they kind of split themselves up into, specialized subgroups. That was actually our hypothesis, was that division of labor would sort of emerge spontaneously and we would see a huge return to groups that kind of subdivided and specialized. We didn't see that, right? At least no strong evidence of that. And possibly that's because they didn't have enough time, possibly because the task wasn't quite right. A second meaning of your question could be, what about composition of the team, right? So if I first took a bunch of people and ran them through a test and said, okay, or a battery of tests and said, let's assign them a bunch of features, psychometric features and skill features, maybe even demographic features. And now, does diversity in team composition predict performance? And there's a lot of, prior work that suggests that's true, but it hasn't really been tested in this kind of framework. So that is an open question that we're very interested in looking at. Thank you.
Time for one last question. Maybe, yeah, please, at the mic.
Hi. So your work for the group effort, team effort, was really interesting, and but that seemed a little like a lab environment stuff. So do you plan to do similar analysis for real world settings? And if so, would you like to share some insight on how you could set up
how do we make that more real world? Well, so if you compare that task to all the other tasks that people have studied in this field, most of them are sort of people pulling a rope or clapping or shouting or maybe solving a word puzzle. So this is pretty realistic. I mean, it actually is a real thing. There is a whole group, world of people who do crisis mapping, and they have conferences like this one. So in some sense, it is a real task. But I take your point. It doesn't really help us at Microsoft to say, I have software engineers and I have marketing people, and they have they're very highly skilled people with years of training, and how should I put them together to solve some task? We're really still dealing in a world where you can sort of take undifferentiated people and throw them into a group and have them do something, and that is not realistic. So we have some thoughts about how to do that, but obviously it just gets more and more difficult to design and run these things the closer you want to get to reality. But I sort of see this as a progressive thing where you try to sort of use stuff like this as a proof of concept to show that it can be done and to show that it generates interesting results. And then hopefully somebody has the resources and the interest to try to implement a similar type of experiment in an environment that involves real world levels of specialization and sort of consequential outcomes.
So we're out of time, but please join me in thanking Duncan.